All right. Well, good morning, everybody. We'll get the show started. So, welcome to the Friday morning BEG seminar, and we're very fortunate to have our very own Kutalmis Saylam here. Kutalmis has a background in hydrogeomatics engineering and has completed several projects as a principal investigator over the course of his career. He has worked in the public and private sectors and traveled for consulting projects around the world. He is currently employed as a research scientist associate at the Bureau of Economic Geology, Jackson School of Geosciences at the University of Texas at Austin, where he manages the remote sensing and the LIDAR program. His principal research interest is LIDAR bathymetry and performance analysis. In his spare time, he teaches archery and competes in tournaments.
Yes.
Very interesting. Well, welcome and thank you very much, Kutalmis.
Thank you for the introduction. Let me put down my coffee. Well, thank you all for coming. So good to see you Friday morning. So yeah, this talk is a little bit different than the usual Friday seminars in BEG here. So I'm talking, of course, on behalf of our group. So this project that we completed last year in the summertime in the Arctic, myself and Aaron and John, and we had another external helper with us as well. So I'm going to talk a little bit about that. There's a lot of interesting and cool stuff in there, but of course, this is just because we got tons of data of everything, and this is basically we're slowly scratching the surface of what we can do with this. So this project was sponsored by NASA, and the name was by the NASA was given is ICESat-2 Calibration and Validation 2022. Usually NASA has funding for similar researches that relates to global warming and sea ice and glacier melting, glaciology, cryospheric science, and all that. I'm because of course, it's global warming and sea level is rising with melting of ice and all that. It is a cool science, and well, hopefully we will get something really useful out of it. Okay, let's just begin. So what exactly was the motivation, and what kind of science questions do we need to answer at the end of this research study? So the principal motivation was, I will talk about that a little later. NASA has a satellite altimeter that orbits and shoots LIDAR laser around the world, basically in the orbit, but it is meant to provide height differences and find height differences of the glaciers and the sea ice principally. But we are not aware of course, they have tested many times how accurate it is finding the heights and measurement, but they never had any kind of testing on the sea ice. So what we wanted to do is basically find out how accurate the measurements are working with the satellite altimeter. Of course, those are fundamental questions. So there are other, so there is 3 altimeters involved in this research. One of them is a satellite, and there's 2 airborne. And they will all correlate. They all need to correlate to each other. And so sea ice is basically a floating ice on the sea, but there is you will see pictures of it later. There are ponds that occur on it in the summertime because of the melting of ice, and those are called melt ponds. And they really wanted to know also the depth of these melt ponds, because every year in the summertime, so the depth is associated with also global warming. So of course, we're talking about dynamic surfaces. The sea ice is drifting very fast. So even though we are measuring the ice, we also wanted to know, is there any way that we can also calculate how fast they are shifting, and can we apply the rotational parameters into our calculations. Of course, some of these are not even in the contract with NASA, but those are some of the science questions we brought it up. Because there's a lot of coincident and a lot of related data in this research, so we also wanted to bring machine learning methods to predict some of the sea heights that were not exactly measured or available. And also, I will talk about that also later too, because the satellite altimeter is on top of atmosphere shooting, wavelengths. It is, there are atmospheric influences that apply to the wavelength. And so when we are comparing things, we need to basically take those into consideration. So here's a introduction for materials. There is, like I said, there is 3 sensors in this research. The first one is ICESat-2. So it was launched in September 2018, and the principal mission was to observe, like I said, the melting ice sheet and glaciers, and relate them to global warming studies and to predict sea level rise. And you can see here, use this. So this one is, we're talking about Arctic here. This is March 2019, 2020, and 2021. These measurements are done by ICESat-2, and then you can see, of course, the sea ice thickness is actually decreasing, which is, of course, worrisome to all of us. So there is the second sensor is LVIS, which is Land Vegetation and Ice Sensor. This is an airborne sensor. This sensor was in the same platform as our sensor, so it was a good cross-check for us. It's also this sensor is an in-house built system, and it is a kind of a prototype that they test their laser before they put it on satellites. Basically, it is a high altitude system. Even though it's airborne, it can fly really, really high and shoot from really high altitudes. So this one is the Leica Chiroptera. This is a commercial system we used. It is, of course, it's a topographic bathymetric LiDAR system, and it is meant to use at lower altitudes, but it is very accurate because we've been using it for 10 years now. This is not the exact system. We have it here at BEG, but this is one, this is a newer system compared to ours, but it is principally and operationally, it's very similar to what we have. So let's talk about NASA's ICESat-2. So this has, of course, a very powerful laser because it is orbiting at 500 kilometers high and shooting light beams from that altitude. It needs to be very powerful. So it has a near polar orbit, which means there's a little hole here exactly on the polar, so it goes around it. So these yellow dots, so these green lines are the orbits. These yellow lines show you, this is just basically, I just pulled it off just a couple of days ago from their website. The data usually comes after a few months of an operation. So these are the last day that data became available. So they are, you can see that they are not really consistent because in those areas, that means there is no measurements because of, probably because of clouds, high clouds. So it has 3 sets of sensors. They are paired, so there's 6 sensors in it. Their powers are different because so that they can detect low reflectance and high reflectance. And these sensors are 90 meters apart from each other, and there's 3 kilometers between from one end to another. So the problem is I highlighted here when I proposed, hey, we can do this, but the biggest challenge was because the satellite flies or orbiting really high up there, the ground speed is really high. So for us to shoot the same targets at the same time, it's very challenging. So it does 7 kilometers a second is a ground speed, where we are only when we are flying the jet, we are doing 100 meters a second. There is quite a bit difference. And the second biggest challenge is the pulse. So basically, when it's shooting a laser beam, of course, by the time the laser beam hits this ground surface from 500 kilometers, the pulse beam enlarges and the footprint is 13 meters in a radius. So compared to ours, I will talk about that later, it is quite wide, and that's also another challenge. So so there's a website you guys can all go to there and sort of pull some data. It's called Open Altimetry. So ICESat-2 produces different types of data. So this one is called ATLAS number 7. ATLAS number 7 is the data that comes from the polar zones, from North Pole and from South Pole. That's why these dots are there. So there are different ATLAS data types. For example, you want to pull some data when ATLAS is orbiting in the Caribbean. So that's for example, that's ATLAS 9 or 10. There's different kinds of data. It comes with a Python. You need to have a Python code because there is so much information in there. It is because the information is based on a waveform. So you have to have a Python code, and with the Python code, you have to basically extract the data that you need. So this is NASA's LVIS, this the airborne lidar system that we were talking. So right now we are in the aircraft in this picture, and this is 2 scientists here, NASA scientists sitting in front of LVIS. So it is basically another high-powered laser, of course, not as much as ICESat-2, but these guys can also fly quite up high, like 20 kilometers high. And but their laser is only near infrared. It only works in near infrared wavelength compared to Chiroptera. I'll talk about that. And their scanning pattern is, we call this zigzag oscillating scan pattern. It's basically like a Caesar. It goes like this. And they're not this. Also, this sensor is not really meant to fly low altitudes like we do with Leica Chiroptera, because their pulse footprint is adjusted to fly high, so that the pulse footprints can overlap each other, so that they can create a topographic image like this. Also, this data is available on their website. Also, you need a Python code to extract the data that you need, because it also comes with a waveform. So, so this is Leica Chiroptera. It's a commercial system. It's very similar to what we have here. Ours is Chiroptera as well, but the first generation, this is now the first, I think it's the 3rd generation this guy is. Now there's a 4th one. So it is meant to fly in a small aircraft, just like here, like a little Cessna here. It doesn't have to be Cessna, but you know, it's supposed to fly low. You're supposed to fly low, which is 500, 600 meters, 2,000 feet, so that the green wavelength in the system can have a high amplitude to penetrate into the water. So the more if you fly higher, the laser is losing its amplitude to go deeper in the water. So there's 2 wavelengths in the system, the near infrared and the green. They worked in conjunction together. The near infrared is meant to bounce off from the water surface, where the green is supposed to go inside and come back from the depths so that you can calculate the depth of the water surface. So here it is. At 500 meters that we propose to fly at this study, our pulse footprint is for near infrared is only 25 centimeters. So compared to ICESat-2, 13 meters in radius, so much, much, much bigger. right? So there is some when you're comparing things, of course, we need to keep that in mind. So this is the survey aircraft. It's not really meant to be a survey aircraft. This aircraft was owned by Nike executives to fly there around the world and go do their high price businesses. NASA basically grabbed it. It is a Gulfstream. I never flown a Gulfstream before. It was very exciting. But of course, inside is like a laboratory. There is, but of course, in this is, I put it here, there are snacks, there is coffee, and there is lasagna, which Aaron loved it. My first question was when they proposed that, oh, we're going to fly with a Gulfstream, a jet. I said, really? How slow can we go? Because, you know, when we're surveying, we're not supposed to, of course, we shouldn't laser. You know, it's not a really huge deal because with the speed of light. But it really matters on the ground of the point density. So the slowest without the flaps that it could fly was 250 knots, and that worked out pretty good. And another good thing is when you fill the tanks, it can fly for 7,500 miles. It will go from, so we flew from Houston to top of Greenland, like nonstop. So where were we? Even though this project is like Greenland, it's like actually really not really related to Greenland. The survey area was right here. This is North Pole, this is Canada, Greenland. So we did our work here in the Arctic Ocean. But we, of course, that was the closest place that we could stay. And also, you know, Thule Air Force Base is also quasi-American. There is, of course, it is run by Danish and Greenlandic people, and Canadians also use it as well. Very nice base. You have a lot of luxuries that you can think of. So this is the lodging areas. This blue building, I have to tell you about that, is when somebody is COVID, they lock you in that building. And he was, I'll talk about that a little later too. Because that really like a challenge. Okay, so let's talk about those exactly, the challenges. So the first challenge was we had this brand new LiDAR system we never used. We did not even do a calibration. We didn't even go fly on the coast. And are there bugs in, you know, it's electronics, right? There is sometimes bugs, we have to clean those bugs. But because of the NASA bureaucracy and their compliance formalities, we just didn't have time for any of that. So basically, like we were here just, you know, okay, trying to get ready, but we have this brand new system that we never used. We don't even know how to operate it. Of course, we got trained for it, but not in the real scenarios, not in the real environment, not in the wild. So we were very stressed about that. But thinking that, you know, we have something similar and we know how things work, we said, okay, we'll manage it. So, but basically by the time we were able to press fire, we were already in the Arctic Ocean. And okay, so there were quite another, of course, there were quite a few other challenges. The first one of them was when we were there, the Gulfstream avionics broke down, so it had to go all the way from Greenland to back to Houston. Exactly. So it was like that costed us 4 days or 5 days, I can't remember, something like that. And you know, we're up in the north, over on top of Arctic Circle. It's daylight 24 hours a day. So like, you know, I've been doing this quite a while. Whenever there's a daylight, it doesn't matter it's midnight or 7 in the morning, we go fly as long as the weather is good. But because it doesn't work like that in a space, Air Force base, the airport is open 7 a.m. to 4 p.m. And every 7 a.m. there is this fog. that you cannot, there is no approach visibility. So you have to wait for the morning mist to go away. And also, but when you're waiting, you're also missing ICESat-2 flying over you. Anyhow, so also our issue was the bandwidth. I wrote this here, but this is true. The bandwidth was so bad. It was like a 56K dial-up modem. It was, and also we had data limits even in that, like, and we had to purchase. Actually, NASA purchased this for us anyhow. But I remember when Aaron was COVID and locked in the building, and I had to operate the system. We communicated via Instagram's DM. That was the only thing working. Seriously, he basically literally trained me by sending messages from Instagram. Okay, so this is how it looks. So this is what we're surveying. This is a video I will show you. So I'm basically flying it without working. And that's the environment that we're shooting. This is the sea ice in the summertime. Of course, it breaks. Summertime, kind of. That's what we're shooting. So that's what you know. Okay, so so these were the airborne missions. So the ones that are highlighted in yellow are basically the ones that we got really nice data. So these lines are, again, these are ICESat-2 orbits that we're trying to catch. The black ones are the aircraft trajectories that we flew over them. Okay. But the one that really worked for us is the one that is 26th, which was the last day. Okay, so what we did, of course, because we are trying to understand the accuracy here, of course, we had to have a nice calibration, first of all. And of course, in a brand new system, we didn't calibrate before. So that is me with a GPS pole there in the airport. So I was, of course, so some people basically supervised me when I was doing that, and the airport runway was closed, but it was off hours. I think it was a Sunday. Yeah, it was a Sunday morning. So we got 326 control points on the runway, which is right here, so that we can calibrate the LiDAR beams to that surface. So the near infrared and green combined is just like 1 centimeter of accuracy. So this is July 21st, where this is the most data we had. And this is also very nice data because most of these are flight lines. These are SWAT. We call them SWAT, and they are nicely overlapping with each other. So we do this as a general practice also when we are flying here on the coast or somewhere else. But the difference is this is a dynamic surface, meaning by the time you fly one of these lines and turn around and come back, you fly the second line, and the overlapping area, of course, here, in a normal surface which doesn't move, it's identical. But here, everything is different because the ice already shifted, which is a good thing in many ways, so that we can vectorize, find the features and vectorize common features so that we can understand how fast and in which direction the ice has shifted. So this day was a very good day. We had a lot of data, but the problem was you go to Open Altimetry to download the ICESat-2. It's right here. We got no data. That means because there was high clouds over us, the satellite altimeter did not really shoot what we shot. So it didn't work. On the 26th, we got lucky. So this green line is a really nice, good line. We flew northbound when the satellite was coming southbound. And we really caught it by this much. at this location. So the closest basically we got to a coincident exact surface was around 8 minutes. And I think that's a big success. So here it is. If you go to Open Altimetry for that exact location, this is what we got. This is the data. There is good, nice data. And there is 3 pairs of ICESat-2 data. And there is also, we also have the, if there were no low clouds here because we flew over this area, we will be exactly on top of each other, but it didn't work out because the low clouds blocked our measurements. But this data set that we have is actually very useful. So this is how it looks. The Chiroptera also has a very high resolution camera. So by the time it is actually shooting the LiDAR, it's also snapping these high resolution images in 4 bands, in near infrared included. When we stitch these because they are overlapping together like an orthophotography, this is basically, you come up with this beautiful line. This is very high resolution, of course. You may not see the details here, and then you can overlay the LiDAR on top of it. Then you have basically the best of worlds and with heights and everything. So, okay, let's talk about this study a little bit. So what are we doing here? So we are trying to compare, again, data sets with each other on the sea ice surface. And sea ice surface is not a surface like this. It is very zigzaggy with all sorts of heights on it. So it is it's a varying surface. So because we got lots of data and we have I have an algorithm. Basically what it does is, so you tell the algorithm, okay, so draw a radius here, for example, 2 meters, and then extract all the measurements in it, interpolate all the heights and compare to the guy that you want to compare. So in this one, because ICESat-2 pulse footprint was 13 meters wide, radius, so there is like close to 2,000 measurements in it. So the algorithm worked basically find every 13-meter radius of a ICESat-2 measurement. Of course, because of, again, the sea ice surface, it's very zigzaggy, and it created quite a bit of outliers. So basically, the first approach was to clean some of those outliers with a quartile method. And then the second one, the geophysical models that applied, especially, I mean, ours, we're flying at 500 meters high, so we don't consider atmospheric effects that happens to our LiDAR, but ICESat-2 has to go through that. Especially you're shooting a sea ice surface, which on the polar regions, there's a lot of tides that you have to consider. So you can see here, so this is even though this is your mean sea surface, there's a lot of models that go into to calculate just a plain mean sea surface. So usually we go with tide-free geoid. That means because all the heights are here coming from GPS, which are ellipsoid. So we usually convert them to geoid, and then we're usually done, but not in this case. So here, for example, in the Texas coast right here, the geoid is minus, correct me if I'm wrong, John, 23, 22 meters, something like that. But up there in the polar region, it's plus 16, 17, 18 meters. It's quite a bit adjustment in the geoid. Anyhow, so right now, the calculations that I have done for the Chiroptera data set considers, of course, the tidal effects, but there is NASA just introduced a new formula for their inverted barometer. They were just, I was just on a work group meeting and they were just talking about that. So that's going to change some of the measurements here that I haven't accounted yet. So here is, let's have a look at this sea ice drift, what's happening. So for example, on the this one is 23rd, there's these 2 flight lines here, but you can see what's happening with the winds. So there is winds coming from this strait here between, I'm not sure what the straight name here is, 28 kilometers, and there is one that is going eastbound at 15, and of course your your north is this way, your true north, and then you have to calculate. So you have to calculate how this ice has drifted in which direction. Shelby Short, right? She's here. She's been working on this. She's great. So the easy way to, of course, when you have overlapping flight lines like this, the blue and the red are two perfectly overlapping flight lines. It's easy because we can do a vector. We can find a feature, and then we can find that feature in both SWATs, and then we can do do a basic vectorization, and then we can find it. For example, in this one, the timing delta T timing difference was 13 minutes, and then basically we can find the drift. So it was pretty fast. You can see it. It moved 7 meters in a minute in 293 degrees bearing. So the purpose here for doing this, because the only flight lines that were not overlapping was the ones that actually is very useful, the ones on the 26th. So we needed to basically use the overlapping flight line data, get the results, validate the results, and apply those to the 26th, which we haven't done yet. We're not there yet, but we're getting there. So also we downloaded this radar and InSAR. Also, they're coming data sets from Copernicus, from European Union's managed system. So the data comes like this. Like it shows you, for example, in X direction, what happened right here, in Y direction, and what happened. So you have to combine these, and then you have to. So we did this, and we also compared the results that we found with vectorization. So in actually, like you can see, the bearing works perfect. The difference was 1% to 2.8%, and the drift, this was very slow. That's why this is high, but still in the acceptable threshold. But this, you can see, it's like 2%. So now we will apply these drift metrics and the bearing in degrees to the 26th, and we will rotate the data. Anyhow, okay, so this is how it looks when we are shooting the same target, from the same platform. So this is LVIS near infrared versus Chiroptera's near infrared. So this is basically our metric to check if everything is working for us and for them as well. So the gray is a SWAT line of Chiroptera, which is much wider compared to LVIS, but you can see the zigzag feature of LVIS because they are flying very low compared to what they should be flying. That's why you can visually see the scanning pattern. So in one, their footprint at this altitude is 1 meter radius versus ours is again 1/4 of a meter in radius. So there is 9 returns from Chiroptera in 1 meter that we can compare to their one measurement. So the result here on this one is really literally perfect. So you can see your RMSC is like 28 to it's just around an inch, and your R square is just basically perfect. But there is, of course, the orange here is Chiroptera, the blue is LVIS. There is a little bit of shift, which is 25 centimeters. That's because of we're not really applied any atmospherical models that also applies to LVIS. So for example, our data has tide correction, but there's not. So this is also an ongoing investigation, but we're not really worried about that. This is what matters for us. So let's come to the ICESat-2 versus Chiroptera. So now we are comparing, again, this is a satellite. This is an ICESat-2 footprint. You can see how wide it is, 13 meter radius, compared to this little tiny guy, which is ours. So in 13-meter radius, Chiroptera has 1,671, just a number right there, returns. So what the algorithm does, every, you cannot really see it, but so the algorithm basically picks all the heights from all those returns and finds an average and compares to the other guy. And of course, because of, again, we are comparing sea ice surface, which is very zigzaggy, very changing, very variable. So we expect a high standard deviation on this. So what happens is, there you go. So here, for example, there is your ATLAS measurements, like points, right? Just like a little dots here. So this is a cross section. So the reds, can you see it? Yeah, you can see it. Okay, so the reds are the satellite measurement, and near the grays are Chiroptera. They're in a cross section. You can see they're mostly matching. They're on top of each other on a cross section, which is good. But of course, the correlation does not produce this regression here, does not produce a super nice linear regression, because it's not going to. Because you're not exactly because you're comparing one measurement to 1,600 measurements on a very zigzaggy surface, but here the average was basically again 14 centimeters, which again these results are not final. I haven't made all the adjustments, atmospherical adjustments yet. So also here, as you can see, the timing delay on this one, for example, on this example was 12 minutes to 16 minutes. So we will apply that clock delay and rotate our LiDAR data to maybe get even a little better result later on. So here's another one. So this one was their 3R sensor, which is the strong sensor. And this one is their 3L, which is the weak sensor, but the results didn't change as much. It is pretty much the same. So this is your ATLAS measurement here, one line. You cannot really see that, can you? No. So again, there's a cross section here. The lines are exactly on top of each other, but this also shows you the heights of the sea ice surface. It's from here to 66 centimeters to 38, minus 38. So it's like a 1 meter of a change here. But this is your probability, which is really good. So you got RMSC here, 22 centimeters, which is actually pretty good. Okay, so so far so good. So now we are slowly moving along and progressing, and then getting into some other methods of finding, okay, what else can we do? For example, here you can see that. So this is the flight line, and the black line here is the satellite line. What happened is we basically shifted. So even though we were here in the south, we were right on top of each other. The airplane just moved a little bit, and then we basically missed the target line. So here we were just wondering, and another researcher here is working on this. So can we train, because we got lots of coincident and lots of good data, can we use machine learning, and can we train our data, and can we predict the heights in the areas that we basically missed? Looks like yes, we can. We are in the beginning of this research, but when we train the data with 80% here, train 80%, validation 10%, and test 10%, that's just basically this is showing the randomly selected test data. The orange data is the trained data, the blue data is the real data. So the results are pretty much the same. So it looks like it's going to work. But again, this is just started doing this. So we will work on this quite a bit, and then get some real good results as well. So another research just starting is, so we would like to build an automatic feature recognition here, because like I said, these are melt ponds. These are called melt ponds. This is basically a pond, a small lake that is formed on the sea ice. with no connection to the ocean on the bottom. So the depth of these melt ponds is critical for global warming studies. So there are really there are thousands of melt ponds in the sea ice surface, but there are some of these are really large like this. So the SWAT width here is 400 meters here. So this lake is at least 150 meters long. It's pretty big. As you can see, we can vectorize it, and then we can get exactly the depth of this very nicely. So, but we are trying to see if we can build a automatic algorithm that does it automatically for us instead of we do it manually. Okay, so that's pretty much most of the research so far we have done. So the preliminary findings, so the cross-check between our system and their NASA's airborne system is really robust. So that means we are good to go. The correlation between ICESat-2, the satellite altimeter, and us, again, the RMSE, the average of all the measurements is 22 centimeters, which is actually pretty good. And the mean shift is 15 centimeters. That is also not considered. I haven't considered all the atmospherical models yet. That's probably also close up a little bit more. Maybe we will be in sub 10 centimeters range. And like I said, the challenge was we have to understand that we are trying to correlate heights that is on a very varying surface, and also the footprints, the pulse footprint and the point density is really high. So we cannot really expect, and we should not expect perfection in this. Also, the application of machine learning methods so far looking very promising. The test results give us the values, the results that we need, but we will do additional studies on that. So the to-do list, this is still an ongoing research in this. So right now, what I showed you was the satellite altimeter works in green wavelength. And what I showed you was green wavelength versus the near infrared. Now also I will do a green to green comparison, but that will be not on the surface. That will be on bathymetric surfaces like a melt pond. For example, I will compare when the satellite hit a melt pond, what was the depth. And so I will find all those areas that is depth applicable and make a comparison. And we will try to use that sea ice drift metrics that we calculated and try to shift some of our data basically and see if we have a better match with Atlas 2. I don't think it will improve anything, but just for the science of it, why not? This geophysical models that apply to ICESat-2 is a little bit cumbersome. It's also beyond my pay rate, but I'm working on it. There is a little bit of confusion on this and some of these because there's so many different models and that apply to the satellites measurements. And because for us to compare exactly basically it has to be the same. So whatever they're applying, I have to apply the same thing. So I'm also getting there. So hopefully we are talking about doing a similar research also in the South Pole next year. But of course, I think some of that depends on some of the findings that will come from the study. And this data is available, is publicly available because it's NASA federal grant. So it's already out there. Any researcher, anybody who's interested in, there's a beautiful data. You can do a lot of things with it. It's there. So there is the link, and then you can contact me so that I can give you the password. Okay, that's it.
Great, thank you. Thank you, Kutalmis. We've got time for some questions. I see
45 minutes, perfect.
A hand in the back there. Jeff.
That's Jeff.
Oh, I got one here. Yeah, good talk, Kutalmis. So I'm somewhat familiar with this, but it seems like one of the biggest issues you have is trying to separate real differences between the systems versus introduced ones from a moving surface. And would it have been a good idea to collect data over a fixed surface like that is also a satellite track line? And maybe when you go to Antarctica, you could do that where you're getting something where you could take out that
That's
that movement.
Yes, absolutely. That's exactly what we wanted before we go up there. We wanted to test it where exactly on a hard surface that is not dynamic, because the orbit of ICESat-2, it goes over the same surface every 3 months. So we could find an area like in the Gulf Coast, because we were based in Houston. We were looking at areas especially in the Bolivar Peninsula where the ICESat-2 was actually crisscrossing, that we wanted to survey those before we go up to Antarctica. But because of the NASA board did not approve the use of a commercial LiDAR in their system until we got there, we just couldn't do it. That was the issue.
Even in Greenland, there were some ISAT tracks over the island itself, or Greenland, that
Yes,
might have been
absolutely.
good. Yeah.
We shot ice sheet, which is we shot some data over ice sheet, which is of course not moving, which is not dynamic. But again, it was a high pressure environment when you are trying to catch a satellite with all those weather conditions and everything, all those things that we wanted to do exactly what you're saying, we had to basically just skip, because you are trying to catch a satellite that moves 7 kilometers a second in low cloud, high cloud, wind environment where airport closes, where there is people in isolation with COVID. So all those kind of add up, and there were a lot of things that we wanted to do, but we couldn't do it, including exactly what you're saying.
Any other questions? Okay.
Nice talk. So I have a fundamental question. So you use terms like sea ice height versus sea ice thickness. So I mean, my question is, does your measurement include the below water surface part? Like, I mean,
yes, the data includes all that. That's right. But this study is meant to measure the heights on top of the sea ice. Yes, there is data that also penetrated, like you've seen in an image like this. For example, I'll show you here. Because, for example, this LiDAR data here is the near infrared and green together. So wherever there is an opening in the ice, like that black area, of course the laser goes through it. But the other thing is, because of LiDAR here, the green wavelength likes transparent waters, like so that the light can go deeper. Especially that in those areas, the water is so dark, and so whenever the laser hits those areas, it loses its amplitude very quickly. But of course, I looked at some of the depth penetration, and the water there in that area is 3,000 meters deep. So the laser penetrated to something like 10 meters in some areas. So that was usually in transparent waters, it can go like 20 meters. So I've seen depths 8 to 10 meters deepest. So what you're saying is, of course, so we have the surface, sea surface. We have the data here up on the ice. So of course you can, that's called freeboard, sea ice freeboard. So you can calculate the thickness, which is the freeboard, of the ice from the sea surface. And plus, because this is ice, right? So there is a lot of ice underneath the water. So if there are some returns also that come from the side of the ice underneath the water. So you have some data as well, but not as much, because first of all, you have to find cracks like that, and then the LiDAR has to come really angled to hit the sidewall of the ice. But there are a lot of things you can do, definitely. And by all means, if you are interested in finding something that about ice related, sea ice related, that we can talk about it.
I have an additional question. So the main message from your study is to, were you trying to, did you try to validate the ICESat
Yes.
data?
Yes.
And so basically your conclusion is ICESat is pretty accurate, right? So it's
Yes.
the main message. Okay.
Thanks.
And you also
Mhm.
talk about like a subgrade, like, melting ponds that's probably low the asset footprint, like around I don't know, 100 meter or even smaller than that. So that's kind of like an advantage of those your study, right? To be able to identify
So
smaller features.
the ICESat-2 measurements are 13 meter wide and they are interpolated, but they are every 70 centimeters. So a lot of them are overlapping each other. Like even though here it shows like dot, 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 that's just because of the center. It is 13 meter wide and they are in every 2 feet. So there's a lot of overlap in that. So when you're basically, of course, when it hits a melt pond, which is 100 meters wide, there's quite a bit of a measurement in there with a satellite as well. So that's what I will also try to find those areas and correlate. But the other thing is very challenging is because it's an ice surface. And so we have never measured an ice surface with LiDAR before. So the intensity, especially the reflection coming from the surfaces is very, very different. So it is, I have never worked with any data before that. So there's a lot of understanding and there's a lot of filtration and classification involved in this because usual classifications that works for us in the Gulf Coast is not working here. It's different. There's different classifications and things like that. The amplitudes are very, very different, especially in a melt pond situation, right? In a melt pond, okay, so here's what's happening. So for example, if I survey a swimming pool, open swimming pool here outside, the green laser would never know that it is actually in the water because the water is so clear and also the bottom of the pool is very reflective, right? So you don't even get the sea, you don't even get the surface of the water. The laser just cuts through it and doesn't understand. So ideally, the laser wants a little bit of turbidity plus a little bit of color change so that it understands that it is laser, it is water. So in this case, of course, especially in the melt ponds are clear ice water. So it is difficult to establish the surface and also the resolution because it works as a waveform. Chiroptera does not measure anything shallower than 40 centimeters. The first 40 centimeters, it doesn't resolve because of the pulse return. The first 40 centimeters is usually even is blank. After 40 centimeters, you start to get the returns and depth. And some of these smaller melt ponds are like shallower than 40 centimeters. So that we're after those like deep ones. That one over there, for example, is the depth is like 2.5 meters, which is very, very deep for a melt pond.
I have a question about the surface of the sea ice apart from the melt ponds, and it has to do with sublimation. And the reason I ask it is because in some places where I've been mountaineering, sublimation creates really unbelievably horrible topography.
Mm-hmm.
In fact, in South America, they have a name for the cone-like things. They're called penitentes, and it's a nightmare to walk on if you're doing a glacier trip or something like that.
Right.
It's
Mm-hmm.
just real, few meters of topography created like a stack of road cones
Mm-hmm.
on the surface. So I don't know, do you see any issues with that kind of thing, with something like a incredibly rugose surface not giving you good returns?
There were a lot of surfaces that didn't give any returns whatsoever. And that's because of, again, it is probably related to the dark and very clear waters. The laser didn't even understand it was hitting the water. There was a lot of areas just like that on the image. There are cracks, right? And then we expect that there's a lot of nice returns from it. There is just nothing.
The surface of
As the surface of the ice, again, is on this one, very highly reflective, especially with thousands of small melt ponds. That's very challenging. Laser doesn't understand that it is actually hitting a melt pond, even like a water surface on the sea ice. So those areas come as just like a shallow crevices, but some of them exactly are contain water. So it's quite challenging to understand the sea ice surface on this.
Any additional questions? Michael, can you see on the chat? Is there any questions? No.
Nope.
Just one final
Sure.
question. You guys traveling around in a Gulfstream over the month, is there any truth to the rumor that the LiDAR team will never fly commercial again?
Aaron flew more than I did in the Gulfstream. What my first impression was, that thing takes off. Like, because you're in a big, you first of all, you think that the seats are just like a commercial airline, but commercial airline, you go on the runway and that's slow take off. This thing, it takes off like that. But I don't know. Aaron really liked the microwave lasagna in there. He's and also when he was COVID, it was a bad coincidence, because we were clear to fly, and Aaron is a trained operator. I was just a backup, which I didn't know nearly as much as him. And I said, okay, you're flying tomorrow. And then Aaron was in the isolation. So Aaron, okay, you have to train me right now. But you cannot even he was in isolation. So that's why we use the Instagram. Okay, push this, push that. Make sure you press that. It was difficult. But he had a very nice room with a river view.
All right. Well, thank you everybody for coming this morning, and thank you, Kutalmis, for a very interesting talk.
Thank you.
All right.
Thank you for coming.